Good morning. We are in the Unit 4, Distributions of Random Variables, and today we're going to talk about the binomial distribution, which is one of the most famous types of discrete models. Okay, but before I'm going to talk about the Bernoulli distribution. It is called Bernoulli or dichotomic because the values are just 0 or 1. Okay, and then I'm going to present several examples. Imagine that we pick a microchip in a manufacturing process and we check whether it is correct or defective. So imagine that we assign the value 0 when it is correct and defective when it is, and we assign the value 1 when it is defective. So that would be an example of a column of data being 0 and 1, so that is called a Bernoulli distribution. So in this case, P is the proportion of defective microchips in this example. And another example would be that we throw a die and then we check if the value 5 is obtained or not. So if we obtain the value 5, we assign the value 1, and if not, we assign the value 0. That would be another example. Then in this case, in this example, the value P would be the probability to get the value 5, which would be 1/6. So we define A as an event associated to random experiment. For example, in this example, the event would be that the microchip is defective. Then we have that P is the occurrence of the event. For example, let's assume that we have a value P of 10%. Then the complementary 1 minus P would be the probability of not occurrence of this event, which would be in this example 0.9. Then we define a random variable x being 1 when the event occurs, or 0 when the event does not occur. Okay, so this is an example of a binomial distribution where the probability function is the following. The probability to get a value 1 is P, and the probability to get a value 0 is the complementary, it is 1 minus P. So this is our representation, okay, when it is 0, this is 1 minus P. When this is 1, we get the value P. Okay, so now let's think about the average of this Bernoulli distribution. For this case, we can apply the general formula about mathematical expectation for discrete distributions that I explained in a previous video. Okay, so we have the sum of all possible values of x multiplied by the probability function. So we have the value 1 with a probability of p and the value 0 with a probability of 1 minus p. So we end up that the average is p. Okay, so the average or the expectation of this variable is p. Good. What is the variance? So again, we have this formula for the variance that I explained in a previous video, the expectation of x squared minus m squared. So we have the possible values, which are 1 and 0, 1 squared with a probability of p, plus 0 squared with a probability of 1 minus p. Then we subtract p squared, and then this is the solution of the variance. Okay, we have this information in the math tables. So now let's think about an example. Imagine that we throw 3 dice at the same time, and we define the random variable number of dice with the value 4. Okay, so in this case, we can define 3 Bernoulli variables. For example, we can say, let's say that we have x1 that takes the value 1 when the value is 4 in this first die and 0 otherwise, or let's and so on. Okay, so for example, x3 would be a variable that takes the value 1 when we obtain the value 4 in this third die and 0 otherwise. Okay, so what is interesting in this case is that if we sum these 3 Bernoulli variables, the interpretation is the number of times that we get the value 4 when we throw the 3 die, or the 3 dice. Okay, and then the minimum value of this y variable is 0, and the maximum value is 3. Okay, so we sum. So x ranges from 0 to 1, but the y, the minimum is 0 and the maximum 3. Okay, so this is a binomial distribution. So this is an example to show that the binomial distribution is the sum of Bernoulli distributions. And this is an interesting idea because it helps us to explain the formulas. Okay, So in this case, we will say that in this example, we have a binomial distribution with parameters n equal to 3 and p 1 over 6. Okay, important idea. The binomial is the sum of Bernoulli distributions. Well, so let's continue. Now let's define an event of probability p associated to a random experiment. For example, let's say that the event is to obtain a 4 when we throw a die. Okay, the probability obviously is 1/6. Then let's imagine that we carry out n independent repetitions of this random experiment. For example, 5. So it can be two different possibilities. It can be that we have a single die that we throw 5 times, one single die, or it can be that we have 5 dice which are like identical, and then we throw them at the same time but just once. Okay, so both situations are equivalent. Then we define the random variable as the number of times that the event occurs. And as I explained in the previous slide, the minimum value is 0 and the maximum value is n, when in this case when the 5 dice are the value 4. So one trick to recognize that the distribution is binomial is that the minimum is 0 and the maximum is n. Okay, this is like an important trick. If we have a discrete variable that ranges from 0 to infinite, this is a different kind of distribution. So if we have a discrete distribution that clearly there is like a maximum and upper boundary, this is the trick to recognize that this is binomial. Okay, so we can define the variable as number of times that the value 4 is obtained when throwing 5 dice. Okay, so that would be, or which is equivalent, or 1 die 5 times. Okay, so in this example, we will say that the random variable x follows a binomial distribution, and this kind of distribution has two parameters, has n and p. N would be the maximum value, and p is the probability of the event. In this case, we will say the symbol. The random variable follows a binomial distribution, n equal 5 and p equal to 1/6. This is a special symbol that we use in statistics. It means we don't say x equal. No, it's not exactly that. We say that x follows a certain type of distribution. We use this symbol. Okay, so property of the binomial distribution. So if we have x1 following a binomial distribution and x2 another binomial distribution, but the value of p is the same in both of them, okay, so if they both are independent and we sum, it turns out that the sum is also another binomial distribution where the value n1 and n2 are summed and the same value of p. This is a property that can be applied in some exercises. Okay, so now what about the probability function of a binomial distribution? Okay, so this is the formula that is like a bit complex, let's say mathematically. It uses a combinatorial number. It's not a fraction. It's not n divided by x. No, it's a combinatorial number that we call n chooses x. Okay, so this combinatorial number is the same as this expression. It is n factorial divided by x factorial multiplied by n minus x factorial. Okay, so this combinatorial number is multiplied by the value of p powered to x multiplied by 1 minus p powered to n minus x. Okay, yes, so for example, in this case, imagine that we want to calculate the probability that this binomial distribution takes exactly the value 3. Okay, so that would be the combinatorial number 5 chooses 3 multiplied by the value of p 1/6 powered to 3 multiplied by 1 minus p powered to 5 minus 3. Okay, so we make the calculation and we get the solution. This is the probability function for the different values from 0 to 5, and in this case we can find that the maximum value is accomplished or is reached at the same time for 0 and 1. We can see that for x equal 3, this value is the one that is obtained applying this equation. Okay, so let's now think about the following exercise. Okay, now imagine that we want to compute probability calculation with the binomial, and then we have to compute the combinatorial number 120 chooses 3. Okay, so we have to apply the formula here that I have just talked about, and then it is 100 factorial. What happens? This number is very, very big. So if you take a calculator and you put 120 factorial, it gives you an error, okay, because it's too much bigger than the maximum value allowed by most calculators, okay. Then how can we do that? Okay, well, so the way to solve this is the following. So we have to apply the recurrent property of the factorial. What does it mean? So 120 factorial is 120 multiplied by 119 multiplied by 119 multiplied by 117 factorial. Okay, and then divided by 3 factorial, which is 3 multiplied by 2 multiplied by 117 factorial. So it becomes that both amounts, which are big, are cancelled, and then finally we end up with an easy calculation that can be obtained with any kind of calculator. Okay, so so this is the way how we should solve this. Good. So remember that the binomial is the sum of Bernoulli distributions. Okay, and then we can use this property. So what is the average of a binomial? The average of a binomial, okay, this is the expectation of x1 plus x2 until xn, okay, then this is n times the expectation of a Bernoulli. And I explained in previous slides that the expectation of a Bernoulli is p, so we end up with n multiplied by p, okay, so that's it. So the average or the mean is n multiplied by p. And what is the variance? So we apply this property. The variance of a sum of independent variables is the sum of the variances. As the variance is the same, we end up with n times the variance of x. The variance of a Bernoulli is p multiplied by 1 minus p, so this would be the variance of a binomial. Good. And so this is the shape of the probability function, and then it is interesting that the shape is not always the same. When we change the values n and the values p, this shape changes. For example, this would be with n equals 6 and p equal 0.1. So the maximum value is reached for x equals 0. But, for example, when n equals 10 and p equals 0.2, the maximum is reached for x equals 2. Or, for example, when n equals 40 and p equals 0.2, this is a totally different shape. Okay, and here we can see that the shape more or less resembles the bell of Gauss. Okay, it resembles more or less like a normal distribution. So in certain cases, the shape of the probability function looks like a normal model. In those cases, we will be able to apply so we will be able to compute probabilities of a binomial, assuming that it can be considered like similar to a normal. Okay. So this topic of normal approximations will be the matter of a video that you can see in the next classes. Okay, so here, okay, for example, the probability that x is bigger than 10, that can be computed assuming that it is similar shape like a model, a normal model. Okay, well, so now let's discuss this kind of exercise. Imagine that we have 6 consecutive throws of a die. What is the probability to obtain 5 at least once? Okay, so sorry, so we have to define this variable. X will be the number of 5 that we obtain when we throw one die 6 times. Okay, then this variable would be a binomial, n equals 6, which is the maximum value. The probability would be 1 divided by 6. Okay, then you have to think that the question that is asked is actually the probability that this random variable is higher or equal to 1. It means to be 1, 2, 3, 4, 5, and 6. Okay, so we could apply the probability function that I explained in the previous slides, that number of times from 1 to 6. Okay, but if we apply the complementary event, it makes much shorter. Okay, the complementary event would be 1 minus the probability to be exactly 0. So in this way, we just have to apply the probability function just once. So we apply the formula. So any combinatorial number over 0 is 1. This is also 1, and we end up that this is the solution. Good. Okay. And another exercise could be the following. Imagine that 100 has a probability of 40% to hit a target. If the hunter shoots 3 times, what is the probability to hit the target at least once? Okay, good. So the event would be that the hunter hits with the first shot. We can define the second event that the hunter hits with the second shot, and another event that it hits with a third shot. Okay. Then the probability of the 3 events would be the same, 40%. So in this case, the probability that is asking is the probability of the union, okay? The probability of the union of the 3 events. Okay, so to make this easier, we apply the complementary, and then we apply the Morgan's law, and then this will be, as the probability is the same, assuming that they are independent. So this is the product of the probabilities, and the 3 probabilities are the same. This is 1 minus the probability of no way power to 3, which becomes finally the solution 0.78. Okay, we assume that the events are independent. What does it mean in practice? Okay, so it means that, for example, imagine that the hunter hits the first shot and he fails. Okay, so maybe in practice it can be that he becomes slightly nervous. So imagine that then he shoots a second time, and then imagine that he fails again. Okay, so perhaps or probably he becomes more nervous. So what happens is that then that affects the probability of success of the third time. Okay, so in that case would be a real example that the events are not independent, but this is not assumed here. We assume that the 3 events are independent. It means that although he fails or not, that does not affect the probability of the second shot or of the third shot. Okay, but this exercise is interesting, but because it can be also solved according to discrete variables. So we can define a discrete variable like the number of times that the hunter hits the target with 3 shots. The minimum would be 0, the maximum would be 3, so it is a binomial distribution with n equal 3, and p would be the probability to hit the target, probability of success, which is 40%. Okay, so in this case, the question is to compute the probability that this random variable is higher or equal than 1. So like in the previous exercise, we use the complementary because the calculation is much shorter. This is 1 minus the probability to be exactly 0. Okay, so for here, we apply the probability function, and we end up that the calculation is exactly the same. Obviously, we get the same solution. It is just a nice example to show that this probability can be computed as an exercise of probability calculations or as an exercise of discrete variables. Okay, well, so here we finish this unit about the binomial distribution, and that's all. Thank you very much for your attention.